Every year, roughly 50,000 ships cross the world's oceans, carrying about 90% of everything traded between countries. Your phone, your clothes, the fuel in your car, almost everything you own spend time on one of these vessels. And underneath every single one of them, hidden below the waterline, is a coat of paint doing a job so important that without it, the global shipping industry would lose hundreds of billions of dollars a year. Most people assume the red color is just tradition, a design choice left over from some old naval custom. That's not quite wrong, but it's nowhere close to the full story. The red color is the side effect of a chemical arms race between humans and the ocean that has been running for over 3,000 years, and we still haven't won it. To understand why that paint exists at all, you first need to understand what happens to a ship hull within minutes of touching seawater. It starts invisibly. Before a single barnacle or mussel ever arrives, a thin film of bacteria settles on the hull's surface. This biofilm, barely thicker than a human hair, is essentially a welcome mat. It changes the chemical properties of the surface, making it easier for larger organisms to grab hold. Within days, algae spores arrive. Within weeks, barnacles show up, their larvae drifting through the water until they touch the hull and cement themselves down, with a glue so strong that researchers are actively trying to reverse engineer it for use in medicine. Within months, mussels, tube worms, sea squirts, and dozens of other organisms pile on top of each other, turning a smooth steel surface into something resembling a reef. The entire process has a name, biofouling, and it is one of the oldest, most expensive, and most persistent engineering problems in maritime history. The drag created by a heavily fouled hull is not a minor inconvenience. A ship carrying enough barnacles to cover its bottom can lose between 20 and 60% of its efficiency in the water. To maintain the same speed, its engines burn dramatically more fuel, sometimes up to 40% more. Multiply that across the global fleet, and you're talking about enormous additional fuel costs and an equally enormous additional output of greenhouse gases. Before antifouling technology, wooden ships had to be dragged out of the water every few months for what sailors called breaming, scraping and burning the hull clean. Entire naval battles in the age of sail were influenced by which fleet's hulls were cleaner and therefore faster. A fouled warship was a slower warship, and a slower warship lost. The first serious solution didn't come from chemistry, it came from the copper mines of Wales. In the mid-1700s, British shipbuilders began nailing thin sheets of copper directly to the wooden hulls of their vessels. The logic was straightforward. Copper is toxic to most marine organisms. The ions it releases into the water around the hull create an environment where barnacle larvae simply can't survive long enough to attach.
The famous clipper ship Cutty Sark, preserved today in dry dock at Greenwich in London, still has its original copper sheathing visible, one of the clearest surviving examples of the technology that dominated shipbuilding for over a century. When iron and steel ships replaced wooden ones in the 19th century, nailing copper sheets became impractical, but the principle remained the same. The solution was to take the copper and suspend it in paint. Cuprous oxide, a compound of copper, turns paint a distinctive deep red color. That's where the color comes from. Not tradition, not decoration. It's the natural pigment of the active chemical doing the actual work. When those early copper-based paints were mixed and applied, they were red by chemical necessity. Shipbuilders and dry dock workers needed to see clearly which areas below the waterline had been coated. Red stood out against the steel hull in the gray-green of harbor water. It stuck. For most of the 20th century, the copper approach worked well enough. Then, in the 1960s, paint manufacturers developed what seemed like a significant improvement: tributyl tin, or TBT. It was cheaper than copper, even more effective, and could be applied more easily. By the 1970s, TBT antifouling paints had taken over most of the industry. Then marine biologists started noticing something alarming in harbors around the world. Female oysters were developing male reproductive organs. Imposex, The growth of male sex characteristics in female shellfish was appearing in populations near busy shipping lanes at rates that couldn't be explained by anything except the water chemistry. Dog whelks, a common marine snail, were going effectively sterile in harbors where shipping traffic was heavy. The culprit turned out to be TBT leaching from ship holes into harbor water, where it was disrupting the endocrine systems of shellfish, even at concentrations measured in parts per trillion. TBT was and is one of the most toxic substances ever deliberately introduced into the marine environment, and the shipping industry had been applying it to every hull in the global fleet for decades. The International Maritime Organization banned it in 2001, with full enforcement by 2008. So, the industry went back to copper. But copper comes with its own problems that are becoming harder to ignore. Ships arriving in port shed copper into harbor water. In busy ports like San Diego, researchers have measured copper concentrations high enough to harm the marine ecosystems in the immediate vicinity.
Several jurisdictions have already restricted or are considering restricting copper-based antifouling paints, which puts the industry in a familiar bind. The thing keeping the global supply chain running efficiently also happens to be poisoning the water it runs through. This is the problem researchers are currently trying to solve, and the solutions being proposed are genuinely strange. One approach abandons the idea of toxicity entirely and focuses instead on texture. Some organisms can't attach to surfaces with certain microscopic patterns. Researchers studying shark skin discovered that its tiny overlapping scales, called denticles, create a surface geometry that makes it extremely difficult for bacteria to form the initial biofilm. Companies are now developing hull coatings that replicate this pattern, entirely non-toxic, working purely through physics rather than chemistry. The problem is that at speeds below a certain threshold, the pattern loses effectiveness, which limits its use to faster vessels. Another approach involves coating hulls with materials derived from proteins found in mussels themselves. Mussels are champion hull foulers. Their own adhesive is one of the strongest biological glues in nature. But certain compounds in their chemistry also happen to repel other organisms. Johns Hopkins researchers have been developing paintable protein coatings that essentially trick marine organisms into finding the hull unattractive without releasing any toxins at all. A third approach sounds almost like science fiction. Researchers are experimenting with hulls that generate weak electric fields across their surface, making attachment physiologically difficult for barnacle larvae without harming anything in the surrounding water. Early results in lab conditions are promising, but scaling to a 300-meter cargo ship hull at sea remains a different challenge entirely. So, the answer to why ships have red bottoms is really the answer to a much older question. How do you stop the ocean from slowly eating your ship? For 3,000 years, the best answer humans found was poison. The red color is just what that particular poison looks like. Today, the industry is searching for a better answer, one that keeps 50,000 ships moving efficiently across the world's oceans without quietly destroying the environment those oceans contain. The next time you see a ship in dry dock with that familiar red hull exposed above the waterline, remember that you're looking at the most recent chapter of a problem humanity has been fighting since the first wooden boat touched saltwater. We've tried copper sheets, arsenic, mercury, tin, radioactive compounds, and sophisticated polymer chemistry. The ocean has beaten all of them eventually. The barnacles are still here. We're still painting. If this kind of story where the answer to a simple question goes somewhere completely unexpected is the kind of thing you want more of, stick around and let me know in the comments. If you were the engineer asked to solve this problem right now, which approach would you bet on? The shark skin pattern, the protein coating, or something else entirely?